Hello. Okay, someone gave a probabilistic method for calculating this, which there might be, but the one you're describing, I think doesn't really have, well, a well-founded ground, because I don't think that multiplying that way will give you the exact number of colorings. Okay, yes, the answer is probably quite obvious by now. I mean, to guess the answer is probably quite obvious by now. And here I've actually drawn every single possible coloring for a 3 by 3 square. And 2459 doesn't work. Oh wait, did I color it wrongly? Oh yeah, sorry. That should be this one, this one, this one, this one, and this one. Yeah. So okay, so someone guessed the answer would be 2 to the n minus 1 squared. And why is that? So think of it. If this really were the answer, where does it guide you? So what does it suggest to you that you should look at? Like, how does this number come about? Pairs, rotations. Well, you can do pairing. Oh, is the problem asking us to let all columns and rows have 0, 2? Yes. Every row and column must have an even number of black squares. So 0, 2, 4, 6, 8. Yeah, amount of squares. So naturally, there will be an even number of black squares everywhere. But you want, how did you get this? The total number of colorings is this, obviously, 2 to the n squared. Oh, you thought, okay, you thought to be even means to be same. Okay. Well, in mathematics, we normally say when something is even, we say it's an even number. I know in casual English, we normally say even means the same. And yeah, I've been through that process before. No one understood me. But yes, so in maths, normally when we say even, we mean an even number. Oh wait, I forgot to record, right? Oh no, it's still recording. Apparently, I recorded the whole hour of break just now. So all the colorings of the thing. Wait. So all colorings of the thing one less than the amount has a unique solution. Well, it's not exactly one less. It's quite large of a gap, right? N squared, n minus 1 squared. Like, this is for a version of n times n, but this one is n minus 1 times n minus 1. So what do you think this suggests us? Anyone? A smaller square can have one outer layer, making a square 1 unit bigger. satisfying. Smallest. I'm not really sure what you are saying. A smaller. Well, so what's a smaller square and what's an outer layer? Okay. Okay. So you mean all right. So you mean you look at the top left n-1 times n-1 checkerboard, and yes, you basically have to focus on that. So here, let's take a look. This actually suggests us to observe the n-1 times n-1 square on top. So let's look at these squares. And hopefully, it is just a bijection. In other words, however we color the red square, the remaining squares follow uniquely. And let's see. And they are. If you notice, all 16 cases, the red squares are all different. And since it's 16, 16 is 2 to the power of 4, these are all of the possible colorings of the red square. So now we have to prove one thing. We have to prove one thing. Given a coloring of the n-1 times n-1 sub checkerboard, the remaining squares in the nth row and nth column, they are all uniquely determined. So first of all, this n-1 is 1, n-1, 1. Well, these squares here are quite obvious that they are unique. These squares here are quite obvious that they're unique because you just look at the column they are in. If it's an odd number, you just color it black. If it's an even number of black squares, you color it white. So every color here is quite obvious to be determined. But how about the last square? How about the last square? How about the last square? How can we make sure the last square can be filled in with some color? For example, if this last row, if this last column and this last row, one has an odd number of black squares and the other has an even number of black squares, then the red squares would be, the red square there couldn't be colored anything. If an even number of blacks, do white, else do black. Yeah, but the last square here is subjected to two conditions. It must fulfill its column being even and its row being even. So how can we make sure these two areas have the same amount, or at least the same parity amount of black squares? Anyone has a proof or even a counter example for this? So the question is, does the number of squares here and here have the same parity? So either they are both even or both odd. Because then and only then we can uniquely determine the last square over here. Inside the red square, if there are odd number of black squares, inside the red square, if there are an odd number of black squares, the corner square is black. If there are okay, yes. So I should probably, because you said red square, I thought you were saying this square, but I think you're saying this square. So yes, it's something to do with the red square here. So let's see. Exactly. So we have region A, let's say this is region A, region B, and region C. The number of black squares, I'll just write it in number of black squares in region A must be the same parity as the number of squares in region C, I mean mod 2. Why? Because the squares here are designed such that every row has an even number of black squares. That means A plus C, or I mean the number of black squares in A plus the number of black squares in C must be even. And hence A and C have the same parity. And also the number of squares or number of black squares in region B is the number of black squares in region C. They are equal mod 2 again. And so the number of black squares in region A must have the same parity as the number of black squares in region B. And therefore the last square is always uniquely determined. And hence we are just freely we are just free to color region C in any way possible, and hence there are 2 to the power of n minus 1 squared possible ways of coloring. So freely color. Therefore, the bijection is for any coloring, I map it to the top left n minus 1 coloring, n minus 1 times n minus 1 coloring, and then the reverse direction is proven by this argument. Yep. Okay, let's look at the next one. This one's quite nice also, and is a fairly difficult one. So a subset, a non-empty subset of this is, quote, nice if the following 2 conditions are met. First one, the sum of elements, well, let's say this subset is S. The sum of elements of S is a multiple of 3. And secondly, S does not contain both 1 and 2. But they are allowed to have one of them. They are allowed to have one or none of them. So how many nice subsets are there? In terms of n, of course. So let's look at a few small cases again. So n is, say, 1. then the subset will be obviously 1. Oh, sorry, there's no such set. No such set. N equals 2. Well, no such set either. If it contains 1 only, then the sum is 1, not a multiple of 3. If it contains 2 only, not a multiple of 3. If it contains both 1 and 2, it violates the second condition. Square brackets n. Well, again, it is, since the start of the section, it is always 1, 2, 3 until n. Yeah, I'll not spoil the answer first. So n equals 3. We have exactly 1, which is 3. Right. So there's 0 here, 0 here, 1 here, which is already quite weird. And n equals 4, we have we have 3 again. And then if 4 is involved, then what can we have? 4, one, no, 2, 4, multiple of 3. And 2, 3, 4, also multiple of 3. Anything else? I think it's just 3. And so on. Yeah, I'm not gonna write that case. So how do we count such subsets? How do we count such subsets? In fact, I will not spoil the answer first. I will give you guys a minimum working time of at least 3 minutes so that I don't spoon feed the answer to everyone whenever someone gets it. So I'll give everyone a minimum working time of 3 minutes, and then we'll come back and see if anyone has any ideas that we want to share and discuss. So we'll discuss at 11:21. So a few people found it. And it's not 3 times 2 to the power of n, I think. In fact, 3 times 2 to the power of n is kind of more than the total number of subsets you can have, right? Which is 2 to the power of n. But yeah, so quite a few people got it. It is to do with the remaining n minus 2 elements. So if 1, 2, 3, so on until n. The thing is, if we focus on the last n minus 2 elements, there is one and only one way to add in numbers here to make it a multiple of 3. Because if you want to add a 0 to make it a multiple of 3, you just don't add 1 or 2. If you want to add 1 to make it a multiple of 3, you just add in 1. If you want to add 2 to make it a multiple of 3, you add in 2. And yeah, so you have a unique determination of the nice subset. For every n minus 2, but for every subset of the remaining n minus 2 elements, you can uniquely add in a subset of 1, 2 to make it a multiple of 3. And one more minor problem is that we want the subset to be non-empty, and therefore we must exclude the empty set case, right? Because if we choose the empty set, then we should have the empty set here to make it a multiple of 3. So the answer would be the number of subsets from 3 to n, which is 2 to the n minus 1. And then I subtract one empty set. Yeah. Because every single subset here will work. So you don't have to times 3. I'm not sure why you times 3. Care to share why you times 3? So because I want to see also where you went wrong, so we can kind of. Oh wait, sorry. N minus 2. Sorry. N minus 2. N minus. sorry. Yeah, we want the remaining n minus 2, right? So 2 to the power n minus 2. Of course, the case for n equals 1 is a bit separate because kind of doesn't really make sense to talk about the remaining n minus 2 elements for n equals 1. So for n equals 2, 3, 4, 5, 6, and so on, it is this. So for n greater than or equal to 2, and then 0 for n equals 1. Yes. Yeah, that's the correct proof. It's the same proof here. So yeah. Okay, let's do the next one. The next one is quite a famous problem. If you have any experience with primary school math Olympiad, which I don't, well, much. So we have a spider web. Let's say a 3 times 5 spider web. And a spider will start at this point, and move to this point. So A to B. And the only directions it can move in is up and right. So basically the spider is impatient. It wants to get to B in the shortest distance. It can only go up and right. So how many ways are there for the spider to go from A to B? So yeah, okay, someone gave a proof here. So you need to move exactly m ups and n rights. The ways is how, the number of ways is how, yeah. So yeah, so that's, well, there are two ways you can do it. One is the recursion way, which many people I know kind of prefers, but it only works for small numbers. So there are two ways you can do this. The first way is I mark every point. I mark at every point the number of ways that they can reach there. So for example, this point has only one way that you can reach, which is by going up from this point. And here, there's only one way you can reach, 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 one, and one. And now for every point here, for every point on the web, let's say this point, you can reach it from the left or from the bottom. So if there are A ways, you can go to this point, and there are B ways you can go to this point. Then there must be A plus B ways that you can go to that following point, because those are the only entrances you can go from. You can go from the left or the bottom. And so by doing this recursive relation, you can write every single number now. So 1 plus 1 is 2, 1 plus 2 is 3, 1 plus 3 is 4, 2 plus 1 is 3, 3 plus 3 is 6, 4 plus 6 is 10, this is 4, 10, 20, 5, 6, 15, 21, 35, and 54. So 54 is the answer using this method. But of course, this method doesn't work when you have kind of 1000 times 1000. Yeah, so a better way would be to take a bijection. And what's the bijection? Whenever the spider moves up, I'll just draw an up arrow. And whenever it turns right, I'll just draw a right arrow. So for example, if I move in this fashion, then the path of the spider would be written as right, right, up, right, up, right, right, up. And notice, in the end, you must have 3 up arrows and 5 right arrows. 3 up arrows and 5 right arrows. So that means you basically want a bijection now. You have the set of paths that you can take and the set of arrangements of these 8 symbols. So you just want to count how many arrangements are there for these 8 symbols. And how many are there? It's quite easy to calculate. There are 8 terms here, so that's 8 factorial. 5 of them are the same. You want to count them as equal, divide by 5 factorial. 3 of them are the same, divide by 3 factorial. And you can write it as 8 choose 5 or 8 choose 3 if you want. So using this method, we can generalize quite easily to the m times n case. So if this is m units and this is n units, very quickly we can find that the answer would be m plus n. Choose m. Yep. Okay, so now the spacing is a bit weird on the handout, but okay, let's start with exercise 9 then. Exercise 9 is something quite related also. So you start off with $50 in your game. Start with $50 in your game. And you toss a coin every round. If you get hits, if you get hits, you add 1 to your possession. If you get tails, subtract 1 from your possession. Okay, so now we have a very specific scenario we're going to look at. You want to see how many ways, how many possible scenarios there are, so that you tossed 100 coins. You tossed 100 coins, end up with 50 again. End up with 50 again. And also one more, just to make things very difficult. You never dropped below 20. So you can touch 20, you never went below 20. So 3 conditions have to be met, and you want the number of scenarios that satisfy this. So 100 coins tossed. This one is a fairly difficult problem. You can think of it. Let's say about 5 to 10 minutes. I'll give 10 minutes actually. So we'll discuss it at 11:42. If you are stuck, you can think about the easier problem, which is you remove the third condition, the last condition. So if you're stuck, you can just ignore the third condition first, and then after you solve the version where you have the first 2 conditions, then you try to move on to include the third condition. Okay, okay. So one person solved the easier version, so without the third condition. Anyone else? Okay, yeah, okay. I saw a few answers, and yes, they are all correct. Without that third thing, oh, it's not 2 to the power 100. It's not 2 to the power 100. Well, without the second thing, it would be 2 to the 100, because every coin you toss, it could be a head or a tail, but you want to make sure you end up with $50 again. And oh, I mean, this one is the first one, this one is the second one, this one is the third one. Yes, the answer would be 100 choose 50 if the third condition is non-existent. And the anyone? Why is it 100 choose 50? Because you want, yes, you want 50 heads and 50 tails. You want 50 heads and 50, sorry, 50 heads and 50 tails. So you want to rearrange those combinations, so 100 choose 50. But to incorporate the third condition, we have to visualize this. So the first and second condition says that if we draw a diagram, let's say we start at 50, let's say the y-axis is how many dollars you have. And after one throw, you could have gotten 51 or 52. And afterwards, you could have gotten 50 again or 50. Sorry, this is, what am I saying? This is 49. And this is 52. This is 48. And you would get a spider web problem again. So if I draw it, if I rotate it about 45 degrees clockwise, we get such a thing. We get a 50 by 50 square. 50 by 50 square. And you start here, you want to end up here, and therefore you have 50 plus 50, choose 50. So that's fine. But you want it to never drop below $20. So let's see where $20 is. So this is 50. 50. And you have 49. And so on. This is 1. So 20 is around here where there will be 20 squares. Of course, I couldn't draw a 50 by 50 grid. So let's say this is where it's 20 squares. So this is 20. So you want it to never cross this line. It can be on the line. You just want it to not cross the line. So you basically want to cut off this portion of the grid. And you allow the spider or you to traverse around about inside this red, whatever shape this is. And how do we do that? Well, I claim that it's easier to find the number of paths that cross the line. So without any conditions, it will be 100 choose 50. And we want to subtract the number of paths that cross the line. Well, if a path does cross the line, that means it kind of must be inside here, isn't it? We can just ignore this portion of the graph now. it must be here. So if the path crosses the line, so let's say like this, like that, like that, like that. So that will be a path that crosses the line. So how can we find the number of paths that cross the line? And remember, there are 20 there. It's not 3 squares. There are 20 squares there. The thing is, if it crosses the line, it must touch this yellow line. First of all, it must touch the yellow line. It must touch the yellow line. If it crosses the red line. Any ideas how to calculate the number of paths that crosses the red line? I'll give you a hint. It's about a bijection as well. Calculating using this diagram will be very difficult. You have to transform this diagram into something equivalent. How to get to the 50 starting from points in the band area. Okay, but in the band area there are many points. There are many points. There are around 20 squared over 2 points, right? Because the side length is a 20 by 20 rectangle. But you can't possibly add up that many sums. The border of the band area. Okay. But let's say you calculate the number of ways to get from this point to the end. But first of all, there are even like 20 points on the line itself. And once you calculate that, you still have to calculate the number of ways to go from here to here, which is more than one. You want to multiply by the number of ways to go from there to there. So again, it might be technically possible, theoretically possible to write out such a sum, but it's going to be very, very tough because you have kind of about 20 points on the yellow line, and for every single point you have to multiply the number of ways to get there and the number of ways to get from there to the end. 0 minus 20. What does that mean? Yeah. Okay. No one got it yet. So I guess I'll just review the answer. So the answer is for any path that crosses the red line, okay, first of all, it must touch the yellow line at some point. So consider that first point that it crosses, which is here. The first point that it touches the yellow line. The first point that it touches the yellow line. And now I reflect across the yellow line the remaining path. It'll be something like this now. And I guess So once I touch the yellow line, whatever's after it, I reflect across the yellow line. And now what do we see? Oh, sorry. That's sorry, this is a bit wrong. If I reflect across the yellow line, in fact, I'll just have this. It will be a path of some very thin rectangle. I mean, not very thin because this is actually, I think it's around 19 or 20 squares. But in the end, you kind of bijected this path into a path of another spider web with a rectangular web. And is this a bijection? Let's see. Given the one on the left, we have the procedure to turn it to the right. Given the one on the right, wherever it hits the yellow line for the first time, I just reflect it back and we get back the one on the left. So this is a bijection. It's absolutely a bijection. And what are the dimensions of this modified rectangle? Let's see. We have to be careful because we don't want to be plus or minus 1 wrong. So we reflect. So how many are there here? So there are 19 squares here. 19 squares here. Because the yellow line is it's like 1 square to the left of the red line. And therefore, there are 100 minus 19, that would be 81 squares here. And so if I reflect it, there will be 81 squares here. There will be 100 squares here. And there would be 19 squares here. So this is a 19 times 181 square. It should be 50 minus 19. Oh, yeah, sorry. That's absolutely correct. It's not 81, it is 31. Thank you very much. So that would be 50, I forgot, sorry. 50 plus 31, that's going to be 81. So it's an 81 times 19 square. And what are the number of paths for this? M plus n, choose m, right? So there'll be 100. What if the blue line crosses the yellow? What do you mean? Like, you mean the second time, the blue line? Because we are counting the number of blue lines that actually crosses the yellow line. So you mean it just touches the yellow line? You can still reflect it. For example, if the path is like this, forgive me for my very, very messy diagram. Let's say it's like that. I can still reflect it. It will become like this. Wait, sorry, no, like this. What if it goes through the yellow line? Then still, whatever's after I touch the yellow line, I just reflect it. What if it goes through the yellow line? So you mean, okay, I cannot really remove. There we go. Like this, let's say like that. Then again, I define it so that after I first touch the yellow line, I just reflect this. Then that would be, I'll just use red for now. Like that. So same thing, I just reflect whatever's after the first time I touch the yellow line. Yeah. Okay, so now we are almost done. You get 100 choose 50, minus 100, choose 81 or choose 19. And this is the answer. So this is a very, very intricate, very subtle, very smart, very ingenious bijection. And this is what you are expected to think of when you are either in junior or senior level, especially in senior level. So you have to think of a very nice, very smart bijection that can simplify the problem. But of course, you have to practice more to achieve that sort of level. Right, let's just skip the last problem and let's try that as homework, because I really want to finish the whole handout by today, and we only have 1 hour left. The last problem, I assure you, is not more difficult than the one we just did. It's an easier one. I'm not sure why I put it as the last one. Probably I had to put it in the wrong place or something. No, you don't have to hand in the homework. You don't have to hand in the homework. It's just for you to practice at home. If you're interested, and if you're interested in knowing the answer or you want a hint, you can just probably message me on Discord or something, and I will try my best to free my time to answer you. So whenever I'm free, I'll just try to reply. Last question is fun. It is not particularly difficult, but you have to think of a bijection. Okay. So the next section is about what I like to call PIE. So the principle of inclusion and exclusion, or the inclusion-exclusion principle. So before we do that, let's just restart the whiteboard. So the principle of inclusion and exclusion is where I want to find the cardinality of a union of multiple sets. So let's say we have a set A and a set B. We have a set A and a set B. And then we want to find the union of A and B. Let's look at a Venn diagram. So if this is A and this is B, and we want the union of A and B, well, it's quite obvious that if you add up both cardinalities, you not necessarily get the answer, because you will double count whatever's in between, isn't it? So you have to subtract once. You have to subtract once the intersection of both sets. So this is the PIE for 2 sets. And our goal is to look at the PIE for n sets. So for three sets, it's fine. Also fairly simple, but you have to think a little bit more. So if you add up the 3 particular sets cardinality, let's see what is double counted and what is triple counted. These big leaves are counted twice, and the one in the middle is obviously counted thrice. So let's just subtract A intersect B and B intersect C and A intersect C. Now, the one in the middle suddenly vanishes because we subtracted that many. So we just add back A intersect B intersect C. Okay, so this is the 3-set version of PIE. And do we see a pattern here? Do we see a pattern here? It looks like we are first adding the singletons, as I was called. So the single ones. So A itself, B itself, C itself. And then I subtract the pairs, the intersection of the pairs. So A and B, B and C, A and C. And then I add the triples. And since in the 2-set version there is no triple, we stop there. But in the 3-set version, we have a triple, so we add 1. And since there's only 3 sets, there's only one kind of triple. So the reasonable generalization is for 4 sets, we do the same thing. We add the singletons, subtract the pairs, add the triples, subtract the quadruples. And that is actually true. It is true for the n set case as well. Add the singletons, subtract the pairs, add the triples, subtract the quadruples, add the quintuples, and so on and so on. But how do we prove that? How do we prove that? In the handout, I gave 2 proofs. You can look at it very. You can read it carefully. I will kind of skip the proofs for now because, well, it's a very lengthy proof, and I presented 2 kinds of methods you can prove this theorem or principle or whatever you want to call it. And one of them is by using combinatorial sums. Which is quite fun in its own right. And the second method is induction. So we go from the 2-set to the 3-set to the 4-set to the 5-set and so on. But yeah, so it's a very small topic that I just want to cover very briefly, if I may. So now, assuming we know PIE, let's just look at the one single exercise that we have in that section. Oh, sorry, the one at the back, not De Morgan's laws. The one at the back. So exercise 12. Exercise 12. So we want to find the number of derangements. So we define to you there what a derangement is. Derangement is a permutation with no fixed points. Permutation with no fixed points. So imagine you have a house and you have 100 people inside, all of them wearing their own hats, and suddenly there's an earthquake, and the hats get jumbled up, and everyone just randomly picks a hat and run. So how many ways are there where every single person does not get back his own hat? Well, his or her own hat. That's basically a derangement. So the goal is to find if there are n people, or the n version, how many derangements are there? So here's how we do it. Well, if I ask you a permutation with one fixed point, the first one, let's say, with one fixed point, that's easy to calculate, right? Because let's say you just fix one, and then you just permute the remaining n-1 elements. Because I just say with at least one, well, how should I say this? Okay, I let A n be the set of permutations where n is a fixed point. Sorry, I should put k because n is the total number, where k is a fixed point. Oh, someone give a recursive relation, but I want to directly find a general form for this. So I let AK be the set of permutations. Sorry, this is already a set notation. Permutations where k is a fixed point. So I fix k. I don't care whether I fix the other ones. I just want to fix k. So a derangement is where I take this. So n factorial minus the set of A1 union A2 union dot 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 union AN. So yes, so AK has obviously n minus 1 factorial elements. That's quite obvious, right? So AK, the cardinality of AK is n minus 1 factorial because you just fix one point and then you just rearrange the others. But now we want this. So n factorial is the total number of permutations. You subtract all possible permutations that has at least one fixed point. That would be the answer, right? If anyone's in doubt, has a question, please tell me to stop because I'm gonna move on. So this is what we want to calculate. Oh, what is a fixed point? So a fixed point is where A stays where it is. So A gets moved to A. So like it's like 1, 2, 3. If I permute it as 1, 3, 2, then 1 is a fixed point because it is fixed where it is. But let's say 1, 2, 3, I permute it to 2, 3, 1, then there are no fixed points. And if 1, 2, 3 gets permuted to 1, 2, 3, then all of them are fixed points. So a derangement is a permutation with no fixed points. And let AK be the set of permutations where K, the element K, not like how many numbers there are, the element K is a fixed point. So now we just want to find this. The total number of things minus all possible permutations with at least one fixed point. And let's see. So AK has obviously n minus 1 factorial elements. How about if I say AI intersect AJ, where I and J are different? I'm just gonna skip writing that. I and J are different. Oh, what is the A1 union A2 union A3? This is the set of all permutations with at least one fixed point. Because AK is a set of permutations where K is a fixed point. If I union them all, this will be the set of all permutations with some fixed point in general, right? Because if it has a fixed point, it must be either 1 or 2 or 3 or some of them. Yeah. And so now let's look at this smaller problem. AI intersect AJ, where I and J are different. I should probably write that. Otherwise, you might be confused. Where I and J are different. So how many elements are there here? N minus 1 factorial. Well, I think it's just n minus 2 factorial, right? Wait, is it the same thing? N minus 2 factorial, n minus. Yeah, it's just n minus 2 factorial because you're just fixing I and J. It is a permutation where I is a fixed point and J is a fixed point. So you're just permuting the remaining elements. So there's n minus 2 factorial, right? Oh, okay, you read it as union. Okay, I see. So we want the intersection because now here we have a union of n elements and we know PIE kind of transforms everything into intersections. And we know intersections are quite easy to compute here. And if we have 3 different sets and we intersect them, the cardinality will be n minus 3 factorial and so on and so forth, right? So now we can kind of compute this quite nicely. So by PIE, first of all, you're adding the cardinality of A1 plus the cardinality of A2 plus the cardinality of A3 and so on. But they are all n minus 1 factorial, right? So it's just, well, n times n minus 1 factorial. Is the derangement denoted as, yeah, but I don't really care about the notation, but some people do write it like this. So this is the number of derangements with n total numbers. But yeah, let's just continue computing this. Now I subtract the intersection of the pairs I subtract the intersection of the pairs. But how many pairs are there? And every pair is just n minus 2 factorial. How many pairs are there? N choose 2, right? N choose 2. And then n minus 2 factorial. So what's the third term? The third term is n choose 3 triples. Every triple's intersection's cardinality is n minus 3 factorial. And so on. Until we reach like the last term where it is 1. But let's see, this thing I think we can simplify by a whole lot. In fact, let's look at the general term. The general term is n choose k, and then n minus k factorial. But remember what n choose k is. It's just n factorial over k factorial n minus k factorial. So we kind of cancel that. We're just left with n factorial over k factorial. Therefore, okay, let's just factorize all of the n factorials out. Then we get 1 over 1 factorial minus 1 over 2 factorial plus 1 over 3 factorial, and so on. Until the last term, which I'm lazy to write, but I think it's something like this. Okay. So how do we write this? That's basically everything that we can simplify. That's the final form. I mean, you can cancel all the first two terms, the n factorial and the factorial, but there isn't really a nice way to write this. There is, however, a way that you can write this term here, because this thing is actually, if you've but you're not required to know this. This thing is almost exactly 1 minus 2 factorial plus 3 factorial, so on. Let's say this goes to infinity, right? Let's say this goes to infinity. So we not just stop at n. We go further, like n plus 1 factorial, n plus 2 factorial, n plus 3 factorial. But if you notice, if I continue this sum with n plus 1 factorial and n plus 2 factorials, I multiply with n factorial, those numbers are very, very small. In the end, they are very, very small, less than a half, definitely. You can just approximate it as a GP or something, the remaining terms. But if anyone here knows what this is, does anyone know what this number is? This is, well, it's something to do with e. Yes, it's 1 minus e to the minus 1. Because e is actually, well, e to the x. I don't require anyone here to know what e to the power x is, but there is a formula for this. So it's 1 minus 1 over 1x plus 1 over 2x plus 1 over 2x squared minus 1 over 3x. Well, yeah, e has a decimal expansion, but I don't really like the decimal definition of it. This should be the actual definition for e to the power of x. And then the fact that this function is multiplicative allows us to define what e is, which is when we put x equals 1. And here we just, well, you can kind of see that this is 1 minus e to the minus 1. So this is almost and very close to, the error is less than 0.5, definitely. Yes, it is the Taylor series, in particular the Maclaurin series. But you don't have to know this. I'm just doing this for fun. You can just end it at this row. But this would be 1 minus e to the 1 minus 1 over e. and this is n factorial over e. So the answer to the number of derangement is actually the closest integer, which I will write like that, of n factorial over e, which is quite nice, interestingly. Okay, so that's for derangements. Let's just move on. Well, you rarely have to use this, but you have to know just for just in case. Well, so the next thing I want to talk about is pigeonhole principle, and it is a very, very large topic. In fact, combinatorics is very large anyway. There are many more topics that you have to learn, including graph theory, pigeonhole principle, game theory, and well, I forgot, but yeah, stuff like that. So what's pigeonhole principle? Pigeonhole principle. Anyone knows what pigeonhole principle is? Sorry. Yeah, if there are more pigeons than holes, one of the holes must have at least 2 pigeons. Pigeonhole principle. Okay, the most general form is this. If there are m pigeons and n pigeonholes, then at least one hole has more than or equal to the ceiling of m over n pigeons. Why is that true? Why is that true? Well, we prove by contrapositive. Let's assume the result is false, and then we will show that there are less than m pigeons. So if every hole, right, it's proof. Well, let's prove the easier version first. If there are n plus 1 pigeonholes, then there is at least one hole with at least 2 pigeons. That's obvious, but I would like you to think of a formal proof of that. We try not to say something is obvious, because you might say, oh, the extreme case is where every single hole has 1 pigeon, and then you have to add one more where so one of the holes must have 2. The thing is, how do you know the extreme case is where every hole has a pigeon? I mean, here it's quite obvious, but not all problems allow you to say something is an extreme case, and you have to define what extreme case is also. So if there are n plus 1 pigeons and n pigeonholes, at least one has 2 pigeons. Why? Assuming every hole has at most 1 pigeon, then I add them up, I can only have at most n pigeons. That's for the small case. So the general proof, if all holes, when is the test? I am not sure. I am not sure when the test is, but you guys can look at the schedule. If all holes have less than or equal to m over n minus 1 pigeons, this is notably less than m over n, quite obviously. So adding up, there are less than m over n times n, which is m pigeons, which is a contradiction because there are exactly n pigeons. So that's a very short proof. It's a very obvious principle, but the implications are very, very large. And you will find it appear in places that you've never expected it to be. So let's try. Well, of course, there's an infinite version. If there are infinitely many pigeons, then one of the hosts has infinitely many pigeons. That one's obvious also. But let's try the few examples given in the exercises. Let's try the first exercise. Let n be any odd number not divisible by 5. Prove that one of 111, 111, and so on. This is an infinite sequence. Prove that one of them is divisible by n. Is divisible by n. The obvious reason why we exclude even numbers and multiples of 5 is because they are obviously not even numbers and multiples of 5. So how would you prove that one of these numbers is divisible by n? Let's not use a number theoretic proof for this. Let's not use a number theoretic proof for this. By number theoretic, I mean you use things like Euler's theorem, Fermat's little theorem, and so on. There are infinitely many numbers. Doesn't mean that one of them must be divisible by n. Like if I choose n to be 5, which is of course not allowed in the question, you cannot use the same argument and say there are infinitely many numbers, so one of them must be divisible by 5, right? Yes, there are infinitely. You're just asking whether there are infinitely many numbers, is it? Oh yeah, yes, there are infinitely many numbers in this list. So n is any number apart from 2 and 5. N is any number not divisible by 2 and 5. So n is not 4 as well, n is not 5, n is not 15, n is not 369,555, for example. So n is any number not divisible by 2 and 5. Or 2 or 5. I mean, yeah. So how do we find this? How is it possible that one of them must be divisible by n? Like if I give n to be a very weird number, like 7713425678900123789, very large number. It's not very obvious that that list must contain a multiple of that number, right? Well, it is true, and why? Oops, sorry. There are infinitely many numbers and each has a finite amount of factors, meaning that at least one is divisible by n. Not a very convincing argument. Like, why does n equals 5 fail in your argument? Each has a finite amount of factors. Well, every number has obviously a finite amount of factors, but for example, none of these are divisible by 5. So why is it specifically divisible by n? It is completely wrong to say if there are infinitely many numbers, it must touch every number once, right? It won't be a convincing argument. So consider each term in the sequence mod n. Yep, I will go back to that. Also, none of 10, 100, 1000 is divisible by n. So it jumps to all amounts, including 0. Well, this kind of wordy proof is also a bit risky because first you have to let the examiner think what you mean, and sometimes if you write it in words, like a very wordy argument and very vague, it will be quite hard to to make it complete as a proof. So we want a very certain and 100% proof of this fact. Like you said, it jumps to all amounts, and why does it jump to all amounts? And what do you mean by all amounts? Like you have to also mention. So please be as rigorous as possible in your proofs and try to make it clear and concise and neat for you for the examiner to read. Okay. All right. So consider each term in the sequence mod n is the best idea. So mod n, if anyone doesn't know what mod n means remainder when divided by n. So remainder when divided by n. So here there are infinitely many numbers, right? So two of them must have the same remainder mod n. This is true by pigeonhole principle because the only remainders you can have is 0 to n minus 1, isn't it? 0 to n minus 1. Finitely many use of infinite pigeonhole. So two of them must have the same. In fact, infinitely many must have the same, but let's just use the weak version. Two of them must be the same. So in fact, if I restrict this number to, I restrict this list to this, the problem still works. The problem still works. N plus 1. Because the reason will be apparent later. If two of them have the same remainder, what do you do? If two of them have the same remainder when divisible by n, what does that mean? So let's say I once and j once, where I is different from j. These two numbers have the same remainder mod n. Yes, that difference is a multiple of n. But what is that difference? Let's say I is greater than j. The difference comes in the form of a bunch of ones followed by a bunch of zeros as well. So this thing is divisible by n. But n has no factors whatsoever related to 2 or 5. So we can just divide by 10. Doesn't matter because n is not divisible by 2 and 5. So this remaining number must be divisible by n. And that's the proof. So again, pigeonhole principle can pop up in any place that you did not expect it to be. This is one of them. This is one of the million times that you will encounter combinatorial problems. Okay, so let's try the next one. Okay, the first few problems is a bit number theoretic. It's also a bit coincidental. I put them together. Among 7 perfect squares, there exist 2 whose difference is divisible by 10. Okay. Among 7 perfect squares, this one is quite easy. There are 2 whose difference is divisible by n. Okay, take the squares mod 10. What do you get? Take the squares mod n. Yes, there are only 6 possible remainders of perfect squares mod 10. And well, this is kind of a number theoretic thing. But let's just check. How do we check? We just have to check 0 squared, which is 0, obviously. 1 squared, 2 squared. In fact, one might say you must check until 9 squared, but in fact, I claim that you just have to check until 5 squared. Because as you will learn in number theory, when you do modulo, you can treat those numbers as like regular integers. So for example, 6 squared, 6 mod 10 is the same as -4. If anyone knows modulo arithmetic, which you will learn eventually, 6 is -4, and -4 squared is 4 squared. Same thing. So I just have to find these numbers, and this is 1, 0, 1, 4, 9, 6, 5, and coincidentally they are all different. I mean, it's not very coincidental, there's a proof of that, but there are 6 possible units for perfect squares, and hence, given 7 of them, 2 of them must have the same. Subtract them and you get a multiple of 10. Yes, that one's a very simple problem. Okay. It's this one. Exercise 15. So S is a set of integers where there are n elements. So a set of n integers, basically. There is a subset, a non-empty subset, of course, of S with sum of elements equal to, divisible by n. Why is that? There is a subset. Well, I can just say a subsum divisible by n. Any idea? Anyone has any ideas how to approach this problem? This is a problem where you cannot force yourself to look at the whole picture. There are many subsets, right? There are 2 to the power of n subsets. Way more than n. But you cannot ensure, you cannot use the previous method. You cannot ensure 2 subsets. You can subtract them and get another subset, right? So what do we do? Find all of the subsets modulo n. Yeah, but how does that help? Because once you know 2 subsets have the same remainder, how can you make sure you can subtract in some way to get a new subset with some elements divisible by n? Okay, so no one got it yet. The key thing is to not just look at the whole picture. We restrict ourselves to a certain family. Okay, someone said elements mod n will be 1 to n minus 1. Add some of the elements. Again, if you have two subsets, you cannot subtract nor add them, because if those two subsets have the same, if they have intersection, you cannot add them up. Find the sum modulo n and remove elements to get it to be divisible by n. But how do you remove? How do you make sure you can remove to get divisible by n? Yes, it's something to do with mod n, but you cannot take it the usual way. And someone got it. So the subset of the first element, first and second element, first, second, and third element, and so on. Yes. So we have to restrict ourselves to a certain family of subsets that we can easily handle. In particular, I will look at, let's say A1. I let A1 be any element in S. And then A1, A2. And then A1, A2, A3, and so on until A1, blah, 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 AN. So why do we restrict ourselves to observe this family of subsets? Because using this list, we can talk about subtraction. You can subtract one from the other. One must contain another. And how many subsets are there? There are n. Okay, but that's not n plus 1. That's not n plus 1. So how? Well, we want a subset that is divisible by n, right? If they are the same remainder, then, well, they are not n plus 1, so we first cannot make sure that there are two equal remainders. But if any of these subsets have a 0 remainder, then we're done, right? If any of these subsets have a 0 remainder, we are done. We just pick that subset. If not, then we have only n minus 1 remainders to choose from, which is 1 to n minus 1. So we have two cases. Case 1. Some hang on. So this is A1, this is A2, this is AN, which is S. So some AI has some, has some 0 mod n. Then we're done. And case 2, the remainders only come from 1 to n minus 1 mod n. But in that case, we have n minus 1 remainders, we have n of them, 2 of them must be the same, and subtract. And yes, that's a proof for this. Okay, let's move on to the next one. Given any 10 points within an equilateral triangle of side length 1, there are 2 whose distance apart is at most 1/3. Okay, let's just change the whiteboard to a, oops, yeah, I do, to triangle. Okay, doesn't help, sorry. So given an equilateral triangle with side length 1, and I just have 10 points inside, how do we make sure that 2 of them are at most 1/3 apart? Again, such a problem, we cannot talk about like very vague extreme cases like, oh, this point must be over there, and then I cannot add this point anymore, and so on and so on. These are very vague proofs, and we don't really accept them. We want very solid proofs where it shows us there must be 2 points. In or on the perimeter. Good question. I don't think it matters. I don't think it matters. Oh, I mean, it can be anywhere inside or on the boundary. It can be inside or on the boundary. Yes, someone said it. Split the triangle into 9 equilateral triangles of side length 1/3. Yep. Is that how I know this? Now there are 9 regions here. 9 regions here. And so 2 of them must lie in the same region. And if 2 of them lies in the same region, obviously their distance is less than 1/3. Okay, when I say obviously, you might ask, okay, why am I saying the word obviously again? But we can prove this very concretely. In an equilateral triangle with side length 1/3 and have 2 points inside. Any idea why we can directly prove? Even if you space 3 on the corner, 6 on the perimeter, there are still lots that are 1/3 apart. Well, again, you cannot kind of use. You cannot say one case is an extreme case without explaining why that is. For example, for a shape which is a very weird shape, it's very hard to determine which points are where you can achieve the largest distance. So let's just be very cautious here. So given any 2 points inside here, what I can do by Pythagoras theorem, the longest length is to put 2 points on the vertices. And okay, but Pythagoras theorem on what? Like how do I know this one is shorter than this one? These 2 segments are, I mean it looks obvious, but if you want to prove it, because sometimes when you draw it, it's not really to scale. How do you relate these 2 segments by, as you quote, Pythagoras theorem? Okay, I think one way you can do it, right? It's the extreme, because if the 7 in the center, if the 7, what's the 7? If the 7 in the center aren't in these positions, then they are either closer to each other or closer to the 3. I'm not sure what you mean by 7 and 3. What's a draw the circumcircle of a triangle? The 3 dots, 7 dots. Well, we're just looking at the 2 dots in a 1/3 triangle now. Yeah. We already passed that stage. There are 9 pigeonholes, the triangle, and have 10 pigeonholes. So 2 of them must lie in a 1/3 equilateral triangle. Now my question is just why do 2 points inside a 1/3 triangle must have distance less than 1/3? Like if it were a square, with 1/3, we cannot make sure. There are 2 points, for example, these 2 points that are more than 1/3. So why is it that if it's a triangle, it works? Okay, there are many ways you can prove this. You can do it by by coordinates if you want, which is very, very overkill. But what I can do is maybe I can draw a line like that. Yes, you can somehow use it, triangle inequality somewhere. And if I draw a line like that, a line must pass through two sides. That's for sure, right? A line must pass through two sides, unless one of them is on the corner, which is even easier if that's the case. Now take the other side which is not touched. Take the other side which is not touched. But anyway, first of all, these 2 points have distance less than these 2 points, right? So we just have to prove that this red segment is less than 1/3. Prove that these 2 red segments is less than 1/3. And now you can do your shifting argument. Now I can shift this red line parallelly to one of the corners, which must exist because the angle is like that. And once we do that, we can extend this again. Now we just have to prove that this new line is less than 1/3. But of course, from this vertex, we move here. Now we can use Pythagoras theorem. Because AB must be less than AC. Now you can use Pythagoras theorem. And now, yeah, then we're done. Because AC is 1/3. So everything before it is less than 1/3. But of course, such a minor detail, it depends on the examiner whether they allow you to skip that. All right. We have 10 minutes left, which is very dangerous. We still have 4 questions. Let's try the next one. Or in fact, let's skip the next one. That one's fairly easy. Let's try the harder ones. 18 is quite a hard one. Prove that among n+1 numbers from the set 1 to 2n, there is one that is divisible by the other. So 1, A1, dot, 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 AN, n+1, sorry. These are all elements of the set 1 to 2n. There are 2 of them that must divide each other. Divisibility is very, very hard to control here because what can you say about divisibility? You want to end up with 2 numbers having one divisible by the other. How do we control divisibility in this case? Like what kind of list of numbers do we act as pigeonholes? You want a list of numbers where given any 2 of them, one is divisible by the other, right? In order to use pigeonhole. So you want a list of numbers and something like that. So what can we do? Yes. So 1, 2, 4, 8 is a choice. Or perhaps split into 1 to n, but n+1 to 2n. But that won't help much, right? If you have n+1 numbers. Okay, 2n is a multiple of n. N is less than n+1. Okay, how does that help? But anyway, okay, so n is included in the subset. Why? one dividing the other doesn't mean one must be a multiple of n. Like for example, 3 and 6 is allowed, and n is like 1000. We want to prove that there are two numbers that so that one is divisible by the other, not that both are divisible by n. Okay, yes, and then you try to multiply everything here by 3. Okay, for every 1 to, okay, let me look at this. For every 1 to n, there is a divisible. For every 1 to n, there is a divisible number in n plus 1 minus 2n, to 2n. Okay, but what if we just skip everything? In fact, no, that let's say n plus 1 to 2n, and I take a prime in that, interval, which exists, by the way, by Bertrand's theorem. From n to 2n, there's always a prime for any n. And then you cannot control it anymore. Oh, you thought the set includes the numbers 1 to n plus 1, but it was actually n plus, oh yeah, n plus 1 elements, sorry, n plus 1 elements in this set. Okay, so the key claim is this. Our pigeonholes are 1, 2, 4, 8. So this is the first pigeonhole. Any two numbers lying inside here, they divide one another, right? So that will be our first pigeonhole. I'm not sure which one it will end, but it will just end at some power of 2 less than 2n, which I don't care what it is. I just let this be the first pigeonhole. The second pigeonhole is, I want to skip everything here. I don't want the pigeonholes to overlap. So the next one I'll take 3, and 3 times 2, and 3 times 4. Again, this is a pigeonhole where if given two numbers inside, they must be divisible by one another. Oh, the next one, 5, right? 5, multiply by 5 again, and then multiply by powers of 2. The next one is 7. And basically, I do all the odd numbers. Not just primes, all the odd numbers. Because, for example, 9 is not yet included. In the end, we have to add 9. So how many pigeonholes are there? 1, 3, 5, 7. In the end, it must be 2n minus 1, because that's the largest odd number that you can have. And of course, in that pigeonhole, there's only one element. So how many pigeonholes are there? There are n, right? N pigeonholes. And all of these are disjoint, and they exhaust every number from 1 to 2n, because any number can be decomposed into an odd part and a power of 2 part, right? So we have n pigeonholes, n plus 1 numbers. 2 of them must lie in the same pigeonhole, and hence one must be divisible by the other. All right. For the last 5 minutes, that's just, I'll briefly, but not prove to you, talk about exercise 19 and 20 and the importance, exercise 19 in particular, the importance of it. So let's look at exercise 19. It's called Dirichlet's theorem. Let alpha be any irrational number and n be any positive integer. There must exist m and n such that this holds. What's the significance of this? This theorem says that any irrational number can be approximated as close as possible to a rational number. So here, as you can see, I'm not writing anything on the whiteboard, by the way, I'm just talking. If you see the inequality, 1 over large n, I can let n be 10,000, 1 million, 1 million to the 1 million to the 1 million to the 1 millionth power. And I will still find a rational number such that m times alpha minus n is less than that distance. And so the fraction n over m would be 1 over 10 to the 10 million to the 10 million to the 10 million to 10 millionth power to alpha. So this is what we call the property where the set of rational numbers is dense. It's dense in the set of real numbers. And by dense, we mean given any interval, as small as possible, we don't care, any interval in the set of real numbers, there must be a rational number inside that interval. That one's a bit hard to prove. So exercise 17, 19, 20, and the previous one, exercise 11, and so on. You can just try it at home because we don't have time to do that. Or you can just, in the following problem-solving sessions, you can just ask them the question, and then maybe they can let you do, and then they will discuss it, because they would definitely know how to solve these four problems. Then for the last 2 minutes, I'm just opening up to any Q&A sessions. Irrational numbers have infinite decimal digits, so it is always possible to find a rational number extremely close. Yeah. Well, let's see. That works. The problem is that the problem of that is it depends on how you define a real number. Actually, it depends on how you define a real number. If your definition is about decimals, then it will work quite nicely. But some people define real numbers as kind of what we call a completion of Q in the standard metric, which I'll not go into. But you can prove it that way. I'll allow it. I'll allow that. But the thing I'm looking for, the proof I'm looking for, is this. I'll just type out the numbers. So this is the list of numbers that you want to consider. Where A, when I type A, I mean alpha. These are all numbers in 0 and 1, and so by pigeonhole principle, 2 of them must lie in some very close interval, and you can do it from there. But yeah, any more questions before we end the class? No, anyone else? I'll open up to any questions related or unrelated to the lecture. Okay, if not, then I hope the best and do well in your test, which I am not sure when it's going to happen. So it will be a few weeks later that I will come back to probably teach something else, probably geometry, I think. So it's been a honor, pleasure, and privilege to be here. So thank you all. I will see you guys next week, next month, I think. Yeah. Okay, goodbye.